Hi everyone. So this week we'll finish up with the multigrid section. I've divided this into two videos. The first one is going to be multigrid cycles and the cost of multigrid, and the second one will be on the different components of multigrid. So last week we only had a look at interpolation and restriction operators, but there's also the coarse grid operator, which we'll look at in that video, and some more details on which smoothers you should use for which methods. At the end of the week, you're also going to get the corresponding programming task. So this week, we're not going to have any code on the slides, since that's essentially your part to do. Okay, let's begin. Last week, we saw a nested iteration, which is implementing in a somewhat naive way the main idea behind multigrid. So using different grids to smooth errors at different frequencies. We also saw that after having solved the coarse problem once, there's still some low frequency components left. And that led us to the idea of finding a way to return to the coarse grid later on in the program by introducing a restriction operator into the algorithm. And using that, we looked at a two-grid algorithm. So this week, we're going to extend that. There's, of course, nothing from stopping us from adding more than two grids. And that's the main idea that I want to cover this week. There's multiple ways of inserting more grids. In this context, we'll cover V and W cycles, as well as the full multigrid cycle, which is sometimes referred to as an F cycle. And then I'll talk about computational effort, so cost per iteration and speed of convergence of multigrid. To start, let's have another look at the two-grid method as we saw it last week. So just as a reminder of what it looked like. We start out by doing a relaxation or smoothing step on the fine system. So this should just be one or two steps, maybe, not more. And it gives us an initial guess for a solution XH, which will still be absolutely terrible. And using that initial guess, we're going to compute the residual equation. So that's R is equal to B, which is the right-hand side, minus A applied to our solution guess XH. And from now on in the algorithm, we work only with the residual equation and not with the equation itself, and use all the contributions that we get as updates to the initial guess XH. So we restrict the residual to our coarse grid. So here the coarse grid is given with a large h and the fine grid is given with a small h. Then we compute a solution to the coarse problem. So this is A with a large H times the error is equal to the residual. And then once we have that solution, we interpolate the coarse grid solution back to the fine grid and add the resulting correction to XH. And then again, we do some relaxation or smoothing on the fine grid. And as we can see now, there's nothing stopping us from doing that same thing recursively. So that's how we get a multigrid method as opposed to a two-grid method. So that's, as I said before, we're doing a two-grid solver, but we're calling it recursively. So that's the entire idea behind the V cycle. We start by doing some pre-smoothing steps. Then we compute the residual. We restrict the residual to a coarser grid. So now this is not the coarse grid anymore, but just one grid level below the one that we're currently at. Then we solve the coarse grid system by using a V cycle. So what does that mean? It means that if we're at the very coarsest level, then we actually solve. But if we're not, then we start again with step 2 and compute the residual and then restrict to one level coarser and so on. If that makes sense. Let's have a look at that on the whiteboard later on. Okay, so to finish going through the algorithm, we then interpolate the coarse solution back to the fine grid, add the resulting correction to X, and do some post-smoothing on the fine grid. Okay, so let's have a look at that. I'll sketch the grids to start with because I think it's a bit clearer with the visualization. So this is our coarsest grid. It only has one interior point. Let's assume that we have 3 grids now. Of course, this continues recursively, so you can have an arbitrary number of grids here. And these are all nested, right? So then we start on this grid and we compute ourselves a solution XL. And we can use that solution to compute the residual on that level. So this is level L. This is level L minus 1. Or L, so that's BL minus XL. So this is solving the equation on level L. And now we're going to apply our procedure recursively. So then we are actually at level L minus 1, and we would do the same thing again. And now, assuming that this is our coarsest level, then we would solve here, and then we would go back up. So what this gives us as a picture kind of is we start at our final level L, we go to L minus 1, and at L minus 1, it's still not the coarsest level, so we continue to, in this case, L minus 2, which is our coarsest level. So at this level we solve, and then we interpolate back. Okay. So there's always here a restriction operator going down these, and then there's a prolongation operator to take us back up. And we can continue doing this for an arbitrary number of grids. Okay, so the V cycle is hopefully clear now, after having looked at it in more detail. So now let's look at the W cycle. If you've understood the basic idea behind the V cycle, then you've also understood the W cycle. The only difference here is that you spend more time on the coarser grids. So in some cases, you have a problem where the coarse grid correction is just not very accurate, and then you need to spend more time solving on the coarse grid before you go back up. So the steps that I showed you before for the V cycle are shown here on the left. So we start at our finest grid, we restrict down all the way until we're at our coarsest grid, solve there, and then we interpolate back up. Well, we start out exactly the same way with the W cycle, only now, once we start interpolating up, we actually go back down, solve again, and then go back up. Go back down, solve again, go back up, go back down, solve again, and then finally end up interpolating all the way back up to our finest grid. So obviously the W cycle is more expensive than the V cycle. I think that's quite clear. You just have more steps. But for some problems in which, as I said before, the coarse grid correction is not very accurate, it really makes sense to do the W cycle instead. Okay. So now what happens if we come back up to the finest grid and our solution is still really, really inaccurate? So we're clearly not done. We have a huge error, or a huge residual rather, because we don't usually know the error. Well, then what you can do is you can just do multiple iterations of the V cycle or of the W cycle. So once you come back up to the fine grid level, you just start another V cycle or you start another W cycle. That's generally what you do. An alternative approach to that is the so-called full multigrid V cycle, which, as I said, is also called an F cycle, which I think just stands for the full in full multigrid. I think with the V cycle and the W cycle, it's quite clear why they're called that, since they kind of look like a V or like a W, respectively. I don't think that the full multigrid cycle, which you can see on the bottom there, looks a lot like an F, so I'm assuming it's just coming from the F in full multigrid. Okay, so in this case, it basically is combining the nested iteration and the V cycle. So again, we perform this recursively. We start on the coarsest grid now instead of starting on the finest grid. And we solve there, and then we perform V cycles always starting in the grid that we're at. So if we're at omega 4h, then we would do a V cycle until we get back to that same level. Then we would interpolate up once again and do a V cycle on that one, and so on until we've reached our finest level. And that's actually a fairly good way of doing this. But which one of these cycles you want to do depends a little bit on your problem, and I guess a little bit on which one you prefer. So all of these get used in practice. You can think, of course, in principle of all sorts of different shapes for a multigrid cycle. You're not restricted to these, but as far as I know, those are the only ones that are used in practice. So now let's think about the computational costs of all of these algorithms. So on the coarsest grid, we actually need to solve. There's multiple ways of doing this, and if the number of unknowns is small, so ideally in the order of 1, which is to say independent of the mesh, then that's really, really cheap, hopefully. So we can do that with a direct solver. As we discussed before, a direct solver scales very badly with number of degrees of freedom, but if the number of degrees of freedom is small, then it's very fast. In fact, it will usually be faster than using a smoother to solve all the way on that grid. So in practice, that's what's usually done. You do a direct solver on that. But you can do a smoother as well if you prefer. Okay, and then the number of smoothing steps taken in between, so on all the other grids, is generally very small, so it should be 1 or 2, and it must not depend on the problem size. That's very important, because otherwise you're going to end up having a factor in your costs that's also depending on n, and then you can't get O of n anymore. So let's look at the computational costs, and we'll look at them on the whiteboard just to see in different dimensions. Okay, so with the computational costs, let's start in 1D. So what are the costs of the full cycle? So let's assume that applying our smoother for 1 or 2 iterations has a cost of c, whatever that number now is. This is not drawing for some reason. Okay, c. There we go. Then a computation on the finest grid has cost n, just kind of by definition, so we assume we have n degrees of freedom on our finest grid. And then to do a full V cycle, this is our coarsest grid, this is our finest grid, I'll draw it with 3 sets. Then here we have a cost of Cn, so here we've halved the total number of grid points to get 1 coarser, so we have a cost of n halves. And on this grid, we've got a cost of n halves again, so that's n quarters c. And if we had more than 3 grids, this would continue like this. Okay, so that's the cost in 1D. In total, this gives us something that's less than 2 times Cn. So it's essentially dominated entirely by the cost of the finest grid. If we do the same thing in 2D, we get something really similar. So now on our finest grid, we have Cn, and for the next grid in 2D, so if this is one grid, then to subdivide, we'd always divide into 4. So this would have 1/4 of the cost, and the next one would have 1/4 again, so 16th, and so on. So this one actually is less than 4/3 Cn. But in principle, the behavior remains the same. The cost is dominated by the cost on the finest grid. And exactly the same thing happens in 3D, unsurprisingly. So we start with Cn, and then now we would divide by 8. Because now if we did this in 3D, and we find in each direction, we get 8 cubes. Okay. And Cn divided by 64. Okay. And again, we can bound this, and it's even closer to just being the finest grid. So essentially in 1D, actually the situation is quite unusual in that we actually have a 2 here. This is going to approach 1 as we continue up in the dimensions. And the basic idea here behind the cost is just the cost is always the cost of the finest grid. So what we've seen now is that the overall cost of the multigrid cycle is dominated by the cost of the finest grid. in total, that gives us per iteration a runtime of O of n, which is what we wanted. But the open question remains how many iterations we need. With smoothers, we saw that while each iteration was only O of n in cost, the total number of iterations depended on n, giving us an overall cost that was much, much higher. But for multigrid, we can actually show that usually the number of iterations is very low, or in fact constant. So in fact, if you're solving sparse systems of equations, linear sparse systems of equations, multigrid is basically the fastest method around. There's a lot of different variations on multigrid, and they get used a lot in practice. But the best possible convergence is often hard to obtain. So for certain equations, this is all a solved problem, and people have already invested a lot of time into finding the perfect multigrid, and then you get what's written here as textbook multigrid efficiency. So if you take the error at iteration m plus 1, then it is smaller than gamma times the error at the previous iteration, where the convergence rate gamma is less than 1. And this gamma does not depend on the total number of unknowns, which means that you always need a certain number of iterations to obtain a certain accuracy, and that number of iterations does not depend on how large your linear system is. Which is to say that if you increase the number of unknowns, you still are left with the O of n convergence, although the exact number differs depending on which problem you're solving. So this is quite astonishing if you think about it, because it means that if you have a system with 10, like a matrix with 10 to the 9 entries, then you can solve this with the same number of multigrid iterations as a tiny 10 by 10 system. So for large problems, that's really very powerful. Although for small problems, you generally would not ever use multigrid. Okay, so let's think about the model problem again. So the model problem here is the Poisson problem that we looked at last week as well. And let's think about what happens if we want to reduce the error by a certain factor, or if we want to reduce the error to a certain truncation level. So if we're thinking about a PDE and the matrix is just a discretization of that PDE, then we know that we have a certain discretization error that we've made just by transforming from a PDE to a matrix system. And there's no point in solving the system of equations more exactly than that error, because then that error will simply dominate. And you still can't get under that error. And in general, for the Poisson problem, actually, this level of truncation of O of h squared for the full multigrid recycle is achieved after just one cycle. So you don't even have to do multiple ones of them. For other problems, it depends a lot on what your problem is. So for other strongly elliptic problems, it's usually okay. In fact, there exist some very general proofs that show the convergence of multigrid is as good as on the previous slide. But for anything that's not elliptic or not linear, you start running into problems. So there do exist multigrid variants for nonlinear problems, for parabolic problems, for hyperbolic problems, and so on. But in that case, every single component of multigrid might fail or lead to slow or no convergence. So that's the smoother, first of all. That one's quite clear. When we looked at the smoothers, we always looked at which matrices it works for. So if you discretize your problem, you can look at the matrix and you can say, oh, this one's diagonally dominant, so I know Jacobi will work. Or, oh, this is not diagonally dominant, so then you know Jacobi won't work. So the analysis of that part is usually fairly straightforward. What can be a lot more difficult is analysis of the interpolation and restriction operators. So we saw last week the one example with the convection diffusion equation in which the restriction operator could lead to slow convergence. And the last component is, of course, the coarse grid operator, which we'll talk about in more detail in the second video. Okay, so in total, achieving textbook efficiency is usually a demanding task for multigrid. But they are very commonly used since they're extremely powerful. Or in other words, it's probably worthwhile to invest a little bit into these solvers.